as I was telling, like in the last class, we discussed the basic building blocks of the discrete signals. So today we will discuss the discrete time sinusoidal signals. So what happens is they have some difference as compared to the continuous counterpart, and so let's discuss what is the difference and how they are defined in the discrete setting. So if you see here, the discrete time sinusoidal signals are basically represented in this way: x of n as a cos omega naught n plus theta. So note here that in the discrete setting, we will be defining the angular frequency omega naught like this. In the continuous setting, it is like this, and in the discrete setting, it will be like this. So when we will move towards the advanced chapters dealing with Fourier series, Fourier transforms, and discrete and continuous, so you have to keep this in mind that we will be using this convention for representing the discrete time for the angular frequency in the discrete signals. So this is this, and this is the phase angle. The important thing is, as you all know, A is the amplitude of the cosine signal, or if it is a sine signal, then it will be the same. Omega naught is the angular frequency in radians. So note here, so it's here it is in radians, and the reason for that to be in radians is because your n here is dimensionless. So n here is dimensionless; it doesn't have any dimensions. So it's basically a scaling index with the time. So n is basically dimensionless. So omega naught will be the radians in order to satisfy this radians unit over here in theta. So this is important point to be noted over here as compared to your continuous counterpart, because there you have radians per second in the continuous time setting. Here we have radians. So another important thing is, this omega naught can be represented as 2 pi f0, and this 2 pi f, in this 2 pi f0, this f0 is again a dimensionless quantity. So it's not having a frequency unit. It will be a dimensionless quantity and is referred to as a normalized frequency. It is referred to as a normalized frequency, and this is a dimensionless quantity. So it's very important to note these points. And again, I will discuss more about this f0 now. So why it is called as a dimensionless quantity and why it is called as normalized frequency in our next slide. But for now, you can keep this in mind. And this is again showing you um, this particular plot, 3 cos omega naught n plus pi by 10. Some example of this is just I wanted to show you example of a discrete time cosine signal, how it looks like. And for different values of omega naught, this is for a particular value of omega naught, this is for the second value of omega naught, this is for third value of omega naught. So for all these three different values of omega, you will have these type of discrete cosine signals. So this is just a simple example for that. So now the important point that comes is the periodicity and non-periodicity of the signals, which is very important distinction between the discrete as well as its continuous counterpart. So a discrete time signal which is given over here is said to be periodic if it satisfies this. So it's as simple as that in case of your continuous setting where we had x of t as x of t plus capital T. So in the same way you have here x of n as x of n plus capital N, where for all the values of integer index n and for a specified value of n not equal to 0, this is valid. And here n is referred to as the period of the signal. So it's as simple as that. You can see here we have a discrete signal, so which has a period of this particular thing. So this is n1, let us say. So this is a period after which this signal repeats. So this is basically the capital N. Okay, so f0, which we are defining here, this f0, it's some problem with the wire, I guess. So are you able to see the screen? Any one of you can just give me a quick feedback on this?
Yes, sir.
Okay. Okay. So here, so f0 is not really a frequency, as I was discussing earlier. So f0 is not really a frequency, but it's a dimensionless quantity and can be thought of as a percentage. So we will see what kind of percentage we are talking about. So here, let us see more about this f0 which we are discussing. So if you have an analog signal or a continuous time signal represented by xat, and that is given as a cos omega naught t, so what we want to do is we want to sample this signal. So regarding the issues of sampling, we will discuss when we will discuss the sampling chapter, but now for time being you can keep this discussion as simple as a normal thing. So what we will do is we will sample a signal at integer multiples of nts. So what we are trying to say is, if you have a signal like this, so we are trying to sample the signal at the discrete intervals like this, and so it will be like ts, then 2ts, then 3ts, then 4ts. So like this we will sample the signal. So we will be sampling at the integer multiples of ts, which is nts. So what we will do is we will just substitute this particular nts into this time period t. So if we substitute this nts into this time period t, what you get is the discrete time signal x of n, which is discrete in time but not in amplitude. Amplitude will remain continuous. So that is one of the important thing to be noted here down. So your x a n t s is basically a cos omega naught, and then you have nts here plus theta. So what you are doing is you are actually substituting instead of small t nts. So this is the one which you have done right now, substitution. So now once you do that, then what you can do is you can expand this omega 0. So omega 0 is basically nothing but 2 pi f0, where f0 is the frequency of the continuous time signal. Then you have nts, right? So ts is a sampling rate. So you can represent in terms of the sampling frequency. So you can just do f of s in the denominator. So it's as simple as that. That is, your ts is 1 by fs. So you just put it there. Now you have this expression here. And now the important thing is, what we will do is we will actually replace this factor which is given over here by f0. So you can see in the numerator as well as the denominator, both of them are frequencies. So why we are saying f0 as a dimensionless quantity? Because the units of frequencies are there in both numerator and denominator, so it cancels out. So we have 2 pi f0 n plus theta. So what we are doing is we are actually representing f0 as f0 plus f0 divided by fs. And also we are representing this 2 pi f0 as omega naught 0 in the discrete setting, which is the angular frequency in radians. So in this way you can see how we have discretized the signal xn as this, with these as the new concepts which are coming up in here. So here f0 is called as a normalized frequency. See, I was telling you the term normalized. Regarding the dimensionless quantity, you already know now why it is called as why it is dimensionless. But for normalized frequency, it is called as normalized frequency because it is essentially a frequency of the continuous time signal. This is the frequency of the continuous time signal which you are actually writing it down here, and then you are dividing it with a sampling rate, which so that's basically a percentage of the sampling rate. Like what percentage of the sampling rate you are doing is basically it is normalized by fs, basically that's why it's called as normalized frequency. And percentage because and it is also called as I was telling you something like this here, right? Some percentage type of word we are using. So this percentage tells that how much percentage your f0 is compared to the sampling frequency fs. So that is basically given over here. So this is basically giving you the insights onto this discrete time signal. So now we will discuss the periodicity of this discrete time sinusoidal signals. So by saying periodicity of the discrete time signals, what we have to do is we have to apply this function, which is apply this particular thing, which is xn is x of n plus n. So we have to apply this condition, and we have discussed what capital N is, and we have discussed the same story in our continuous setting also. So now what you will do is you will actually substitute x of n as this, and then you have x of n plus n on this side. So in order to make the left side equal to the right side, the only thing that you want to see or tackle about is with this factor. So this is the factor which you have to tackle, and you know that cos and sine are 2 pi periodic. So what you can do is you can apply these conditions over here. So if you do it in terms of the 2 pi f0 n, sorry. So this will be equal to 2 pi m, and so from here you can get the value of n as m by f0. So simple, there is nothing fancy about it. So it's a simple equation that you have to keep in mind. But if you want to represent the same, if you want to represent the same in terms of the angular frequency omega naught, so what you have to do is you have to just replace this by omega naught here, and then the value of n that you will get is this. So the important point is you have seen something like this in your continuous setting also. But the only difference here compared to the discrete setting is the extra constraint that we will apply on the discrete signals. And the extra constraint that we have on the discrete signal is that we want our period which is over here, the ones which we are discussing here, because we want to know the periods of the discrete time signals. So we want these periods to be actually integer value. That is the extra constraint that we have to apply on the discrete settings as compared to your as compared to your continuous setting. In continuous setting, the time period t was not having any constraints. So because of this constraint, what happens is, because of this constraints, contrary to your continuous time sinusoidal signals, which are always periodic, a discrete time sinusoidal signal may or may not be periodic. So it depends upon your fundamental period n that you will get from a discrete time signal. If it is not an integer, then what value that you will get will result in a non-periodic signal. But if your n is an integer, then the value that you will get will result in the periodic signal. So the fundamental period is obtained. So note here, the fundamental period that is that you will get from this particular equation is obtained using using smallest integer value of m. So note here that this value which you are actually using for, because this will be from 1 2 3, so it will be like this. So you have to use the smallest integer value of m that will result in n being the integer. So the whatever value that you will get for n being the integer, for that smallest value of m will be your fundamental period, which is here. So because of this additional constraint that I was talking about, that we apply on these time periods, it's not always necessary that the discrete time sinusoidal signal will always be periodic. It will have, it can be non-periodic also. So the signal that we were talking about will not be periodic if the normalized frequency f0 is an irrational number, so that no value of k, it's not k, no value of m produces an integer m. So in this way you can find out the time period of the discrete time setting. So I'll give you few seconds to let me know, like, if you have this periodicity of the signal, to check the periodicity of this signal which is given over here. So if you have a signal which is given as this, which is cos 0.3 pi n minus pi by 10. So can you tell me what is the periodicity of this signal? Like what will be the fundamental period of this signal? Yes.
It is going to be 6.67.
So you are saying that the periodicity of this will be 6.67. So
20 divided by 3.
okay, 20 divided by 3 is what you are saying, and you are saying it's 6.67. But note that we have a constraint, right? We are saying that our capital N has to be integer. So this
So
result
you
should not be right.
multiply it by 3. That will be the answer.
Why you will multiply it by 3?
Integer.
That is true. Yeah, what you are saying is right, but the way you are saying, the explanation you are giving, a bit of it is not that correct. So let me correct it. So answer is time period is 20 here. But let us see how we got it and what are the reasoning behind it. So let me erase this here. So let us say you have this signal, right? So from this you can compare that this is your from this you can compare that this is your omega naught. Everybody is okay with that, because some way or the other we are actually comparing it with this. Sorry, with this. So this is actually omega naught. which is 0.3 pi. So what will be the value of n? So the value of n, if you see this equation which is given over here, so what you have to do, you have to put the value of omega naught here. So you have to put the value of omega naught here. So what you will get is n. N is 2 pi over the value of omega naught times m. So if you see here, what I have written here, 2 pi upon 0.3 pi times m. So it's 20 by 3 m. So now if you go back to the definition, what it says is fundamental period is obtained by using the smallest integer value m, if any, if it is there, that results in capital N being an integer. So based on this definition which is given over here, what we will do, we will actually use m as 3. So if you use m as 3, that is the minimum value of m which makes this capital N integer, as a result of which what will happen, as a result of which your periodicity will be this is not 2 here, 20. So the time period of this is basically 20 samples. So this way you can calculate the time period for the discrete time signals, and this is basically showing you the graph for that. And you can see here that for 20 samples, again after just a second, again the wire is having some problem today. I have to fix this next time. Okay, so what we were discussing was uh, 20 samples here. So as you see, this is the time period of discrete time signal, and after this 20, you will see that these samples repeat again. So from here you can see that n is equal to 20 is the time period for this particular discrete time signal. So let us say if you have these two equations, can you give me answer for both of them, like what will be the time period of this and what will be the time period for this? I am giving you a few minutes to solve this problem. So for the second one, you are saying this is 10. Okay. How about the other person who was talking?
Sir, for the first one, it will be 10 samples for
Okay.
m equal to 1, and the second one, it won't be possible because we won't find a factor of m which can rule out the pi.
Okay. Okay. So let us discuss this so that everybody will be on the same page. So for the first example, as simple as that, you compare it with the 0.2 pi. This is basically your omega naught in the discrete time. So once you apply that constraint which we have already discussed, you will get 10 m here. So what is the minimum value of m that can make this particular signal periodic? So that value is m equal to 1. See, you can put m equal to 2, 3 also, but that will again be not be the fundamental period. It's a repetitive one. So so the fundamental period can be obtained when you put the minimum value of m, which makes this particular factor as an integer. So here n comes out to be 10 samples. So here you see after 10 samples again the signal will repeat. So this you can plot in MATLAB or Python, and you can observe yourself that whether this is indeed true or not. So in this way you can see that for n equal to 10, this will work out. But if you use this particular cosine signal which is given over here, this is not periodic. So in case of continuous time setting, if you use this type of thing, then it will be periodic. But here in discrete time setting, this particular thing will not be periodic because of the constraint that we are applying on the things, like what you are doing, we are taking omega naught as 0.2. So when we apply this definition again, what you get is 10 pi m. So for any value of m, whether you use 1, 2, 3, 4, whatever value you take, it is giving you a value of 10 pi. So 10 pi is again, it's not an integer, and then you are having you want to have n as an integer. So because of this reason, it's not periodic at all. So if you plot this signal, you will see there is no periodicity in this. You can use Python or whatever you want. So based on that, you can see that this function is not periodic at all. So okay, so once you are aware of now that to check whether how this particular signal is periodic or non-periodic, So can you comment upon the periodicity of this signal, like what periodicity this signal will have? You have this signal with you. If I want to know the period of this particular combined signal, what will that be?
Sir, it will be n equal to 25.
N equal to?
25.
Okay.
Getting also same.
Okay. So what you people are saying is 25 is the answer. Okay. So let us see whether it's right or not. So what we will do is, like, you know that these two signals are different. Like one is x1n, another one is x2n. So what I'm saying is, let this be x1 and x2n. So x1n is this and x2n is this. So let us deal with the x1n component. So in x1 component, you have this as your as your omega 1. So the value is 0.45. So from here, what you get is, once you do the calculations, what you will get is the minimum value of m1 is 1, which makes your n1 as 5. And similarly, if you go for x2n, what will happen? We will get a value of 0.48 pi, and then once you solve it, what you get is 25. So as simple as that. And note that the minimum value of m2 that is required to make this particular value of n2 as integer is 6 now. So you can see that it's important that with 6 you are getting n2 as 5, 25. So the total time period that is used to combine, when you combine both of them, is simple. So it will be 25. And actually, if you see, eh, eh, when you simulate this particular thing in Python, or in any of the programming languages that then what you will observe is that what is this 5 indicating? This 5 is indicating that in the total time period of 25, it is repeating 5 times. That the time period is 5, so it will repeat 5 times, as I was discussing in continuous counterpart also. So you can see that for 25 time period, it is repeating 5 times, and the second one is repeating how much times? Second one is repeated 25 times. So the combined period is 25. So when you add the two, you will get this one. This is the answer. So it's a combination of the two, because you are adding them together. So you will get something like this when you plot this in your MATLAB or Python.
Sir, I want to ask,
Yeah.
sir, suppose like if the n1 is 3 and n2 is 2, then will the time period of the samples will be
So
6?
the thing is, you have to use GCD for that. You have to do greatest common divisor, and if that is not coming out, then it will not be there.
So then if we take out GCD of n1 and n2, then it will be 5, not 25.
For where? For this one?
Yes,
Uh-huh. Right, right. It's not GCD. Yeah, yeah, yeah. Right, right.
it might be
Hmm.
LCM.
Yeah, yeah, yeah. It will be LCM, I guess. Yeah. For that case, you have to do that only then. And if it is not coming, like for the two things, when you try to add or multiply, if it not comes, then it will not be possible. Okay, so in case of energy of the discrete time signals, here you have this. If you want to calculate the discrete time signal energy, so how will you calculate it? In again, you have two different parts. One is the real signals, another one is the complex valued signals. So in case of real signals, if you have real signals, then you can do in the same way as we were doing in the case of a continuous setting. So the only difference is now you have discrete xn over here. And similarly, for the complex valued signal, you have, you will take the norm of this xn. So it will be ex here. And similarly, for the power signals also, it will be the same fashion. So in periodic signals, if you are trying to calculate the power, so it will be 1 by n. Then you submit 0 to n minus 1, this x square n. So this is for periodic signals. And for non-periodic signals, what you have to do is you have to take again m tending to infinity. So at that time, we were taking t tending to infinity for that time period t. To make a non-periodic signal, first of all, you make a non-periodic into periodic, and then you move this limit m apart, so that the signal will become non-periodic again. So in this situation also, in discrete time settings, for non-periodic signals, if you want to calculate the power, you will do it by this way. Again, it's the same thing, just repeated in terms of the discrete time setting. For the complex signal also, it will go in the same way. Like here, you will have a periodic signals which is represented like this, and in case of non-periodic signals, it will be like this. Or the only difference is you are taking the norm of the complex number. So I'm not going into the details of the symmetry properties. This we have discussed in details in our earlier lecture on continuous time. So at the best, what I can do is, like, just tell you that what you can do is you can replace xt and x of minus t with their corresponding discrete counterparts. And similarly, if you want to do the x conjugate of t and x conjugate of minus t in the discrete counterparts, it will be like this. So all the discussions that we have done on the symmetry properties related to continuous time signals, whether it's conjugate symmetry or conjugate anti-symmetric, all that discussion on real as well as on complex numbers, same will hold true for discrete settings. With this, uh, with this thing to be kept in mind, that you have to replace the corresponding continuous time with the discrete counterpart. So, this finishes off with your discussion upon discrete as well as the continuous counterparts related to the signals. So whatever manipulations that we have done in continuous and signal in continuous as well as in discrete is finished. So from next time we will start working on systems, because right now when we started the lectures, we told you, like, one part is signal, another is systems. So in the next class we will discuss and we will see how we can characterize the systems which are there, and how they behave, and how can you analyze them along with signals. So in the next class we will start it. So for today's class, I am done. So if you have any questions related to what we have discussed so far, you can ask. Otherwise,